Good morning, all of you. We have learned so many terminology involved in the NMR spectroscopy. The next concept and terminology from NMR spectroscopy is stereochemistry, especially hindered rotation. You know that what do you mean by hindered rotation and when it is come and exist. You also know the stereochemistry of the organic molecule, just like cis and trans compound having the same molecular formula but different arrangement of atom or group, that is called as stereochemistry. So in that topic or in this point, what we are going to learn, first of all I will show you very simple example of ethane molecule. You might have seen that ethane molecules. So this is the stereochemistry of ethane molecule. You observe this molecule very well. Just you look at in photograph, you will find this one. So whatever I am having this molecule, we have here carbon which having the 3 hydrogen atom, another carbon is there which having also 3 hydrogens, and these 2 carbon atoms are connected to the bond, and therefore this molecule become a ethane molecules. So what I want to explain in this case, whenever I am having the rotation, if I rotate one of the carbon atom and another carbon atom is fixed, I can rotate very well, very easily. So I can rotate this one because carbon-carbon single bond having a free rotation. Carbon-carbon single bond having the free rotation. We don't have cis and trans in this case because we can move this very well. You can hold like this and rotate this one. So I am rotating the carbon atom where 3 hydrogen of color, red color are attached. If I rotate this carbon atoms, front carbon atom like this, and if I fix back or behind carbon atom as it is, I can rotate this well. So whatever I am having this rotation between carbon-carbon single bond, this is called as, this is called as free rotation. This is called as free rotation. Means just I applying the energy to the one of the carbon atom and I can rotate this molecule very well. So this is called as carbon-carbon free rotation between 2 atoms consisting only sigma bond. So sigma bond one can rotate very easily between 2 atoms, between the 2 atoms of the molecules. Now if you look at this another molecule, I can see this, you can see this one very well. Whatever I am having this 2 carbon atoms, at one carbon atom 2 hydrogens are attached and another carbon atom again 2 hydrogens are attached, and this is very interesting. Whatever I am having the carbon-carbon double bond, whatever I am having the carbon-carbon double bond, due to carbon-carbon double bond, one cannot have the free rotation just like a carbon-carbon single bond. One is pi bond, another is sigma bond. Both bonds are involved in this one, between this carbon-carbon double bond. When I try to rotate this way, even though I am giving more force to the one of the carbon atom, I cannot rotate very easily. And there is a strain developed between carbon double bond, especially sigma bond and pi bond. And I cannot rotate this very easily because due to the double bond, I cannot rotate this one. Whenever I am having this kind of situation, I can't rotate this bond, 2 bonds simultaneously or at one time. This indicates that this free rotation is not allowed. This free rotation is not allowed. Therefore, it is called as restricted rotation. Therefore, it is called as restricted rotation, or one can say hindered rotation. It is also called as hindered rotation. Another case, if you look at this, this is the free rotation. This is the free rotation. And this is not only, this is happen when we have this kind of molecule having the carbon-carbon double bond, maybe carbon-nitrogen double bond, carbon-oxygen double bond, or carbon-carbon triple bond, carbon-nitrogen triple bond. In that case, free rotation is not allowed, and that is called as hindered rotation or restricted rotation. Another important point is that whenever we are having the bulky group at the different side, again it is little bit difficult to rotate the molecule very well. So whenever carbon-carbon single bond free rotation is not allowed, then it is called as restriction. But if carbon-carbon single bond free rotation allowed, it is called as free rotation. But in single bond, generally free rotation is observed. Hindered rotation will not be observed unless and until they are having a very bulky group. But this is not observed in a simple molecule. Now remember here, what do you mean by hindered rotation? It is a simple phenomena in which carbon-carbon free rotation is not allowed. That is the interesting point. Now see here what things are given in the presentation. The isomer recharge due to the rotation about single bond are called as conformational isomers or conformer. What do you mean by conformer? Also you know that molecule having same molecular formula, number of atoms, number of groups are same, but they are having a different arrangement of groups. If I am having this kind of situation, I can rotate this way. I can rotate this molecule, and due to this, what happened? Whatever hydrogen was there in the initial position, that can change its position. So therefore, you can get conformation isomer when we are having the carbon-carbon free rotation, and it is observed in carbon-carbon single bond. Remember these things. The presence of conformation in the solution cannot be detected by the NMR spectroscopy. Now, whatever we are having the conformation, when I want to explain eclipse conformation and staggered conformation. So this, you know that whenever I am having this situation, means this carbon atom having a zero bond angle between these two groups, then it is called as eclipse conformation. And when I am having the this angle is in 60 degree, not 0 degree, then it is called as staggered conformation. So you can have the staggered and eclipse conformation, and staggered and eclipse conformation which is not detected by the NMR spectroscopy. But at the low temperature, at the temperature much below the room temperature, due to the rate of interconversion of rotational isomer is usually diminished or vanish. And look at this. Whenever I am having the free rotation, because I am having the energy, and due to this energy, I can rotate it, and it is happen at the normal temperature. But if we have this below the normal temperature or low temperature, whatever I am having this rotation, that will not be allowed. So temperature phenomena is again important. When we are having the low temperature below the normal temperature, then this kind of free rotation is not allowed, and in that case you may have the NMR spectroscopy, or NMR can be observed over there. The presence of double bond, especially sigma and pi bond in the compound, it restricts the rotation and result in the formation of cis and trans isomers. Cis and trans isomers are the distinct compound with the different properties in the NMR spectra. In compound where double bond may originate in its equivalent resonating structure, the rate of rotation about the keyboard become a intermediate between free rotation about unhindered or restricted single bond in one structure and hindered rotation about the double bond in the another structure. Consider the spectrum of N-dimethyl formamide at room temperature. What things are given just now? I have explained it, that double bond free rotation is not allowed, but single bond free rotation is allowed. But when single bond is taken and they are having the low temperature, again its free rotation is not allowed. So this is the phenomena that I have explained in the free rotation or restricted rotation. Now see here, this is the example that I want to show you. In this case, this is the well-known example to you, which is called as N-dimethyl formamide. So this is the N-dimethyl formamide. See here, if you look at this N-dimethyl formamide, at one position we have carbonyl group, hydrogen group, nitrogen having a lone pair of electron. Then two methyl groups are there. In this case, two methyl groups, look at this CH3, CH3. Both methyl groups are similar because if you consider this case, nitrogen over here, suppose here is the nitrogen, consider the nitrogen atom like this, and this is the nitrogen, this is the nitrogen. So lone pair present on this nitrogen atom, but nitrogen and oxygen, they are having the free rotation, or single bond is there, sigma bond is there, therefore you can have free rotation very easily. So therefore whatever two methyl groups I have shown here, which is A type, and this another methyl group is of also A type. So both the methyl group of A type, because one can have free rotation very well. Now whatever hydrogen of the carbonyl group is there, it is having another type. Oh, this is called as B type. So A type methyl groups are there and B type hydrogen is there. So three type of proton involved in this compound. So nitrogen, you know that nitrogen having non-bonded pair of electrons, non-bonded pair of electrons, and the lone pair of electrons which is present on the nitrogen atom, which can be moved or transfer from oxygen nitrogen to carbonyl group. Nitrogen to carbonyl group means it is transferred to the oxygen atom. So how it is transferring? Lone pair is transferring like this. I am showing with the help of arrow. You can observe very well here. And ultimately, carbon nitrogen develop the double bond. So again, you will have pi bond and sigma bond. And ultimately, whatever oxygen and carbon bond was there, that again vanishes because pi bond is transferred over here, and oxygen develop a negative charge. So this is it. Present. This is at normal situation. You know that in this compound you can have carbon nitrogen free rotation. Carbon nitrogen free rotation. But when lone pair present of the nitrogen atom, when it is transferred and shifted between carbon and nitrogen, ultimately the bond between oxygen and carbon, pi bond especially, that can transfer to the oxygen atom, and now nitrogen and carbon develop double bond, while oxygen and carbon having a single bond. Look at this in the next structure, you can observe very well. Now this is the actual picture, that after putting that pi electron, or after transferring the lone pair of electron present on nitrogen atom to the next, that is called as resonance, that is called as resonating structure. And in that case, nitrogen develop the positive charge and oxygen develop a negative charge. Now see here in the last compound or last figure, what we have seen, that two methyl groups are having the same nature, showing the same type of carbon atom, because carbon nitrogen free rotation was allowed. But when pair of nitrogen atom, non-bonded pair of nitrogen atom, when it is shifted to the next, definitely carbon nitrogen double bond is developed. So see here, carbon nitrogen double bond is developed, and positive charge is also developed on nitrogen atom, and oxygen develop the negative charge. Now in this case, look at this, whatever I am having the methyl group, so two methyl groups are now different. Two methyl groups are now different, and in this compound there are in all 1, 2, 3 different carbon atoms are there. So look at this, due to this free rotation, you can have AA type, but in this case now we have restricted rotation. Carbon nitrogen double bond present, that is having pi bond and sigma bond. One cannot have a free rotation. Therefore, whatever I am having the methyl group at below the side, it's a different type, and methyl group which are present at the above the side, it is a different one, and hydrogen is different. Now in this case, you can have 3 different type of hydrogen atoms are there. So look at this, restricted rotation and non-restricted rotation or free rotation. Again, I have explained these things by making use of ethene and ethyne. What do you mean by ethene? Carbon containing molecule containing carbon-carbon double bond, that is the ethene, and carbon-carbon triple bond, when it is present in the molecule, then it is called as ethyne. So see here, in case of ethene molecule, carbon-carbon double bond is there. When we have this kind of things, you know that both the carbon atoms are sp3 hybridized carbon atom, and here is the CH bond, and here is the hydrogen in the orbital. Here is a carbon-carbon single bond. One is sigma bond and another is pi bond. So this kind of rotation will not be allowed. And look at this overlapping unhybridized 2p orbitals. No, you know that when you are having the electronic configuration of carbon, you can observe that atomic number of carbon is 6, and you can have the configuration 1s2, 2s2, 2p2. So p orbital is developed, and due to the pi bond and sigma bond, free rotation is not allowed. Now this is about this carbon-carbon double bond, that is in case of ethene molecule, and this due to the presence of carbon-carbon double bond, free rotation is not allowed. Free rotation is not allowed. Now if you consider that this one, that is ethyne molecule, again you will observe that due to the presence of 3 carbon-carbon double bond, one is sigma bond and two are pi bond. So definitely that is not allowed. Means again due to the 2 pi and 1 sigma bond, carbon-carbon triple bond, free rotation is not allowed. So in that case you can say that in ethene and ethyne, restricted rotation is always observed, and this indicates that the hindered rotation. Thus, the NMR spectra for such a compound is usually consist of superimposition or spectra resulting from 2 or more rotational isomers present at equilibrium. Some amide, oxime, nitroso, amine, etc. Now you will have the question: which type of compound will not show the free rotation? You can this kind of rotation you can say amide, then oxide, then nitrosamide, because nitrogen containing lone pair of electron, and that lone pair of electron is transferred to the next carbon atom, especially on oxygen atom or heteroatom, and instead of having that single bond, that makes double bond by the transfer or moment of pair of electrons, and therefore it shows restricted rotation. So amide molecule, oxime molecule, nitrosamine molecules, they always show the restricted rotation, even though they are having a pair of non-bonded pair of electron. Thus, in the spectrum of NN dimethyl formamide shows two non-equivalent methyl groups which observed at a different field strength. The two signals observed doublet for methyl groups, and methyl groups are as a result of coupling with the formyl protons. Now for each doublet, we observed the different value of coupling constant. Proton observed at 1 methyl signals appearing at 7.21 tau value, and that of our other methyl group, or which is showing the doublet, is 7.06 tau value. The value of coupling constant for methyl signals appearing at 7.21 tau is found to be higher. Its position is predicted as a trans with respect to the formyl proton. At elevated temperature, rapid rotation between carbon and nitrogen makes both methyl group magnetically equivalent, and only one signal is observed for both the methylene groups. So see here, what we have explained is that now this is the situation when we have the temperature at higher one, means this amide having the higher temperature. In that case, rate of reaction is increased. It means that whatever I am having the pair of non-bonded pair of electron, that cannot be moved very easily from that, and you can have the free rotation very well. But when we are having the room temperature or below the temperature, in that case, lone pair of electron present on the nitrogen atom, that can easily move to the next carbon atom, and ultimately it moves to the oxygen atom. Therefore, free rotation is not allowed. So at elevated temperature, you will get this kind of situation. But when we have the normal temperature and below the temperature, we can have this kind of picture. Means in this case, both the methyl groups are different, and in this case, both the methyl groups are similar. So remember here, similarity of methyl group and dissimilarity of methyl group. So in this case, methyl groups are equivalent, and in this case, methyl groups are non-equivalent. So this is called as restricted rotation. Now, why this methyl group is showing the doublet? Why this methyl group showing the doublet? Because it is connected to nitrogen atom. As per as n plus 1 rule, n is equal to 0, 0 plus 1, 1 is equal to singlet. So this methyl group should show the singlet. But what happened here? Whatever this methyl group is there, it is going to couple with this proton which are present, which is present at this carbon atom. So this is called as long range coupling. This is called as long range, or you can say that fictional coupling is there. This is called as fictional coupling, and by using this n plus 1 rule, n is equal to 1, so 1 plus 1 2, so therefore this shows doublet, and ultimately this is showing the doublet because again we have this fictional type of coupling, and you can have n plus 1 rule, n is equal to 1, 1 plus 1 is equal to 2, therefore it is showing the doublet. So both are showing the doublet. In this first case, it is showing the cis, and the second stage or second way we have the trans. So you can have cis and trans type of coupling is there, and therefore both methyl groups are different and they are showing the doublet. So this is the phenomena that we have to explain in the restricted rotation. So with this we have finished this restricted rotation, and for the making the presentation I have used the book of Pavia, Introduction of Spectroscopy. Another book that I have taken for the presentation, that is Organic Spectroscopy of P.S. Kalsi book. Third book I have used Elementary Organic Spectroscopy by Y.R. Sharma, and also I have used the internet. So again, this is not used for commercial purpose, it is only for the educational purpose. With this, we have finished this presentation. If you have any problem, any doubt, just ask me. So it is